The next thing that I want to do is I want to introduce a notation which I'm going to call the 1 star x 0 notation. Ask me if I made that title up. Yes. I've never seen that in a, but I think it should be though. So many beautiful, extremely beautiful features of matrix analysis, features of matrix algebra, which we're getting to, rely on exploiting special structure in the location of non-zero elements. So you can get the master's degree in this subject, quite literally. You could spend 2 years studying this subject and you wouldn't even brush the surface of this. There have been people that have been working on this for 60 years. So in this class, we will identify the sparsity structure of a matrix by specifying the location of 0, non-zero, unity. Yeah, I guess 0 and non-zero would be enough. 0 and non-zero entries of our matrix. Specifically, so remember, when we're talking about structure, we're not actually setting the individual coefficients. We're just asking ourselves, where are the zeros? Where are the non-zeros? And is there anything special about those non-zeros? Can you guess how many symbols we're going to use when we're specifying structure like this? 1, 2, 3, 4. If I write a 1 in a particular location, could you guess what that means about the entry there? Is equal to what? Yep. So if I write a 1 in the entry of a matrix, it means that that entry must be equal to 1. If I write a star, this means the entry must be non-zero. If I write an X, means the entry is any real number, which means that it can be non-zero or possibly what? 0. If I want to force an entry to be 0, could you guess what I would write there? 0. So if I write 0, this means the entry in that location must be 0. It's a 0 entry of our matrix. Let's take a look at some examples of things that are going to show up this quarter, in fact, in about 2 days, 2 lecture days. So every single sparsity structure that we're about to throw up here is literally going to come in lesson 10 and 11. So these are all really, really famous sparsity structures. So here are some examples. Examples of what you might call famous sparsity structures. And by the end of this course, we're going to be very intimate with these. What does this particular sparsity structure say? Entry 1, 1 is equal to 1. Entry 1, 2 is equal to 1. 1, 2, 2, 3, 3, 4, 4. Okay, so what we just saw is entry kk equals 1. What do you notice about entry ik if I is less than k? What does it mean for I to be less than k? The row index is less than the column index. Where does that show up in this matrix? One, 2. What do you notice about 1, 2? 1, 3. 1, 4. 2, 4. 2, 4. 2, 3. They're all 0. What about xik if I is greater than k? Yeah, they're x's, meaning to say that they can be any number. They can be real 0 or real non-zero. It doesn't really matter, right? We're going to actually define this thing to be what we call a unit lower triangular matrix in just a second. So this is related to, we'll talk about this, related to LU decomposition. More to come. This is lesson 15 now. But the point is I want to kind of give you an idea of how do we identify this structure, because we'll use this later. All right? What if I told you that we expected a matrix to have this sparsity structure? What would you immediately know? And maybe you need some help. Yeah, go ahead. Yeah, maybe we call it aik equals 1 if I equals k. In this case, what would you say? If the row index equals the column index. Okay, now what? Okay, you want to do it in the same, yeah, I think two of you are on the different stages. So this is a real number if what? K is greater than I. And then this is where Omar kicks in. If the row index greater than the column index, in other words, you're below this thing. Do you see something here?
Diagonal.
Okay. Could you guess what we call that?
Diagonal matrix.
It's not a diagonal matrix. It's called the, but that's a really good guess. Could you guess what a diagonal matrix might require?
Having just a diagonal. Just a metric.
Everything that's not the diagonal of 0.
Yeah.
Sure.
This thing right there, we're going to call the main diagonal, and really I should call this the main diagonal band of a matrix. What is the main diagonal band of a matrix? What's true about it? It is the set of all scalars a, I, k, where I is equal to k. And that's all of them.